Hello, welcome to another module in this massive open online course. So, we are looking at convex functions. We have completed the basic discussion of the basic aspects, including illustration of several practical applications. Let us now focus on some examples to understand these concepts better. Alright, so what we want to start looking at is examples for convex functions. The first example, we want to look at a new concept, which is that of a conjugate, This is a very interesting concept for the following reason, which I am going to describe shortly. But the definition, so given a function f of x bar, the conjugate denoted by the conjugate function f conjugate y bar is this is given as the maximum over the vectors x bar of y bar transpose x bar minus f of x bar. It has a rather very interesting definition, and so this is the definition of the conjugate function. And the interesting aspect of this is this conjugate function is convex even when f of x, the original function, is not convex. This is important aspect. So, the important aspect of this is that the conjugate function f conjugate y bar is convex even if f of x bar is not, even as f of x bar is not convex. So, corresponding to every function, any function f of x bar, convex or non-convex, one can construct an associated convex function, which is a conjugate function, and that is very easy to see. For instance, if we look at f conjugate of y bar, let me just write this again, which is y bar transpose x bar minus f of x bar. Well, you can see that this is a linear in y bar for each x. For each value of x bar, this is a linear function in y bar. So, you are taking, which implies that this is a convex in y bar. And therefore, when you are taking the set, when you take the maximum, you are taking the maximum of a set of convex functions, and therefore, from the property that we have discussed for convex functions, the maximum of a set of convex functions is convex. Therefore, you are taking the set, the maximum of the set of convex functions, that is one function for each x bar, alright, which is convex in y bar for each x bar. You are taking the maximum, and therefore, the resulting function is convex, implies the maximum implies the maximum is convex, okay, and therefore it is convex even if the original function f is not convex. Okay. Let us take an example of this conjugate function. Consider the quadratic function which is f of x bar equals half x bar transpose q x bar, with q equals symmetric positive semi definite, okay, which we have also written as follows: q greater than or equal to 0. Now, if you take to construct the conjugate function, we have f conjugate y bar equals max of over x bar y bar transpose x bar minus f of x bar, which is half x bar transpose, okay. And now to maximize this, let us differentiate this, okay. To maximize this, differentiate and set it equal to 0, we are going to differentiate with respect to x bar, that is, consider its gradient of this quantity, okay. Let us call this as g of x bar, which is differentiated g derivative of g with respect to the vector x bar. And remember, derivative of y bar transpose x bar is of the form c bar transpose x bar, derivative if c bar, which is basically y bar minus half derivative of x bar transpose q x bar. Remember, we said is twice derivative of x bar transpose p x bar is twice p x bar. So, here we have twice q x bar, which is equal to 0. You are setting the derivative equal to 0. This implies y bar equals q x bar. This implies x bar equals q inverse x bar equals q inverse y bar, okay. And the conjugate function f conjugate y equals y bar transpose q inverse y bar minus, that is, y bar transpose into x bar minus half x bar transpose q inverse x bar, which is nothing but basically q inverse, instead of x bar I am substituting y bar, q inverse y bar transpose q times q inverse y bar, which is equal to basically y bar transpose q inverse y bar minus half y bar transpose q inverse into q inverse y bar. So, q inverse and q cancel. So, you again have minus half y bar transpose q inverse y bar. So, that is basically half y bar transpose q inverse y bar, which is basically the conjugate function of and you can see this conjugate function is also quadratic. this is also quadratic, and in fact you can say this is convex. Because Q is positive semi-definite, which implies Q inverse is also positive semi-definite. Remember, that is an important result property of positive semi-definite matrices. If that is, the matrix is positive semi-definite, the inverse is also positive semi-definite. And now you have a quadratic function with a positive semi-definite matrix, and therefore that is Q inverse, and therefore that is also a convex. It is a convex function, that is half y bar transpose Q inverse y bar is a convex function. Okay. And so therefore this is convex, and this is the conjugate function of x bar transpose Q inverse x bar. Okay. So this is something that we have, so one can readily derive the conjugate function. Okay. Let us now look at another example, slightly complicated one, which we want to prove the convexity of the convexity of the following function, where f of x bar equals log k equal to 1 to n e raised to summation e raised to. So, this is log sum of exponentials, it is also referred to as the log of sum of exponentials. It is a very interesting function that arises in several log sum of this is the log sum of exponentials which arises in several applications. What we want to show that this is convex. Show that this function is convex. And for this what we will do is we will compute the Hessian, alright. So, remember the test of convexity, whenever it is differentiable is yet you can compute the Hessian and demonstrate that the Hessian is a positive semi-definite matrix, and that is what we want to do in this problem. We want to compute the Hessian and demonstrate that it is indeed a positive semi-definite matrix, alright. The process is slightly involved, so I urge you to be patient. Okay. So, first let us set for convenience e raised to x k, let us say set this equal to z k. So, I have f of x bar equals log sum of exponentials, that is log, that is basically we can see this is simply log of z1 plus z2 plus zn, which is log, I can write this as 1 bar transpose the vector z bar, where z bar is the vector z1 z2 up to zn, and 1 bar is basically the vector of all ones. So, you are taking simply the, when you are multiplying 1 bar transpose z bar, you are simply taking the sum of all elements of z bar. Okay. And now if you differentiate, that is if you differentiate this with respect to each xi, alright, that is basically you are computing the gradient with respect to x of f of x bar, or rather the ith element. Okay, if you are looking at the gradient, you are looking at the ith element of the gradient. Okay. Now, that would be d by dx, or rather d by dx, derivative with respect to I of your log 1 bar transpose z bar, derivative of log is log x is 1 over, so 1 over 1 bar transpose times the derivative of 1 bar transpose z bar with respect to each xi. Now, in z bar you can see only zi, which is e raised to xi, depends on xi. So, this is 1 over 1 bar transpose z bar into derivative of zi with respect to xi, but recall zi is e raised to xi. So, e raised to xi. So, derivative with respect to xi is e raised to xi only, which is basically zi. So, this reduces to 1 over 1 bar transpose z bar times ci. Okay. So, you have, if you look at the gradient, which is basically the derivative of f of x with respect to each component of derivative of f of x with respect to each component that is equal to, well, z1 z2 up to zn 1 divided by 1 bar transpose z bar, which is basically, you can see this is z bar transpose z bar over 1 bar transpose z bar. That is the gradient of z bar over 1 bar transpose z bar, that is the gradient. Now, let us compute the Hessian. Hessian is the second order derivative. Okay. So, now for the Hessian, first let us look at the derivative with respect to each component xj, that is we have compute the second order components of the form derivative with partial with respect to xi, partial with respect to xj. This is nothing but partial with respect to xj of partial of f of x bar with respect to xi, which is partial with respect to xj of partial with respect to xj of well, what is this quantity? This is, we know the partial with respect to xi, that is your zi divided by 1 bar transpose z bar. Well, partial with respect to xj of zi is 0. So, this is simply, you can write this as minus 1 over 1 bar transpose z bar square into partial of 1 bar transpose z bar with respect to xj, that leaves only zj, which depends on xj. So, that is when you differentiate zj, that is, remember, zj equals e raised to xj. When you differentiate it with respect to xj, you are left with e raised to xj, which is again zj. So, this is, this quantity component is minus zi zj by 1 bar transpose z bar square. Okay. Now, on the other hand, if you compute the second order derivative with respect to xi itself, that is terms of the form partial with second order partial with respect to xi, that is dou square f by dou xi square, that would be second order partial with respect to xi of the first order partial with respect to xi, which is 2 by dou I zi divided by 1 bar transpose z bar. Now, if you differentiate the numerator, we already see in derivative of zi with respect to xi is zi itself. So, that will be zi divided by, well, that will be zi divided by 1 bar transpose z bar minus, now derivative of the numerator. So, 1 bar derivative of the denominator, that is minus 1 over minus 1 over 1 bar transpose z bar square zi times the derivative of zi with respect to xi, or 1 bar transpose z bar with respect to xi, which is again zi. So, this is you have a zi square in the numerator. So, you will have zi divided by 1 bar transpose z bar minus zi square divided by 1 bar transpose z bar whole square. Okay. And now, if I therefore, so these terms are only present in terms of the form dou square f x bar dou xi square, all right. They are not present, if you can look at it, they are not present when you are in the second order terms of the form partial with respect to xi xj. Okay. So, when you write, you can readily see that if you look at the Hessian, that will be, well, what is a Hessian? Hessian is partial of f with respect to x1 square, partial of f with respect to x1, x2, partial of f x with respect to x2, partial with respect to x1, and you have the partial with respect to dou square f by dou x2 square, and so on. And if you put all these terms together, what you will see is, you will see that this is given as 1 over 1 bar transpose z bar times the diagonal terms. Remember the diagonal terms of the form z1, z2, which are only there for the partial, that is terms of the form dou square f by dou xi square. So, z1, z2 up to zn minus terms of the form zi, zj, which can be represented as z bar transpose divided by 1 bar transpose z bar square. So, this is the Hessian of f of x bar. This is the Hessian of x bar. Now, we have to demonstrate to show that this is a positive sim. So, I can also write this as, just one last simplification, this is a diagonal matrix that contains z bar, the vector z bar on its diagonal. I can simply write this as diagonal z bar. So, this is diagonal z bar divided by 1 bar transpose z bar minus z bar transpose divided by 1 bar transpose z bar whole square. All right, this is a Hessian, and we have to show that this is positive semi-definite. To show this is indeed PSD for convexity of f of x bar. That is, we want to show that is this is indeed a positive semi-definite matrix to verify the convexity of this function f of x bar, all right, which we will do in the subsequent module. So, we will stop here. Thank you very much.